All right, welcome everybody. We're in our CCIE Routing and Switching Mentorship Program again, and we are now moving into what I think is a really critical topic from a layer 2 perspective. We've already talked about a lot of the basic concepts. We've gone through the LAN switching and the VLANs and BTP and whatnot. We did a discussion about Ether channel. We really only have a few sections left in the switching group, and then we're going to jump into what I think is obviously the most important aspect, 122 hours of routing topics. But this is what we're focusing on today, is our spanning tree introduction. It says 2 hours. It will probably take close to 2 hours. I know it's already kind of late over there on the East Coast, but so I'll try and get through it as quickly as possible without sacrificing knowledge. That's what we're going to cover today. I did text all the whole group about the rest of the schedule. We're going to try and maintain that schedule. That will definitely get us through the remaining switching topics, and then we're going to start to get into the routing topics towards the end of this week and even into next week. So that's what everybody, I think, is really looking forward to. We're going to be using this topology as usual to discuss our layer 2 topics, and what we're going to be talking about is spanning tree. I'm going to go through some theory, because I think, and I'm going to do a little diagram and kind of demonstrate how the spanning tree election process works and kind of fill in those gaps. Even though that's not really information that you need to know necessarily for the lab exam, you're certainly going to have to know about the theory and the concepts of spanning tree for the written exam. So it's a really important, this is a really important session because it's going to give us the opportunity to kind of identify those specifics. I'm also going to, I was trying to get my stupid Wireshark capture set up on my GNS3, and for some reason it's still not working. So I've got this Wireshark Wiki for the spanning tree protocol. We're going to go through this as well and take a look at the negotiations, what the Bpdus look like, how we can interpret the Bpdus. It's a very, very specific, I mean, it's not really that much in depth because there really aren't a whole lot of pieces of information that are going to go back and forth in spanning tree other than the bridge protocol data unit. So let's get started with the theory. Let me go ahead and open up a notepad document so I can kind of put some notes in here. I'll save these notes in the folder. In fact, let me go ahead and do a save as real quick and save this information in the Google Drive so that you guys can reference this information a little bit later on. Shares, CCIE, and we're doing switching topics, and this is lesson number 10, which is spanning tree protocol. So I'm going to just call this spanning tree fundamentals. So if you guys want to reference these notes a little bit later on, you can. All right, we know that spanning tree protocol is a layer 2 protocol. And I think you guys understand the general purpose of the protocol. It allows us to have physically redundant layer 2 paths in our topology, but removes the loops in the topology. And I'm not going to type everything that I'm writing, obviously, but I want to make sure that we have some of the keynotes in here. The loops in the topology. So we're going to be using our topology to kind of demonstrate the configuration, the concepts, and so on. So actually, let me do one more thing real quick here. I'm going to grab a snippet of our topology. And I'm going to make some notes on here as well. I'll save these images as well as part of the process. And I'll put those in the same folder as we go through the process. So you guys can use this as you're referencing the videos if you want to go back and take a look at the videos. It is kind of important because the The thing about spanning tree is it can be rather complex. The discussion of spanning tree can be rather complex. Configuration and maintenance is relatively simple, but you're definitely going to have to understand the impact of spanning tree. What you're going to have to know for the lab is most likely multiple spanning tree, which we're not going to do today. That's going to be a separate lesson that we're going to go through. But let's get started, okay? So we know it's a layer 2 kind of a link management protocol. It's going to provide us the path redundancy in our topology, and we can see based on this particular topology we have lots of different paths, but it also allows us to prevent loops in the network. And you can see from this topology that we have lots and lots of different loops in the topology. There's a loop there, there's a loop there, there's loops here, there's loops all over the place in this topology. So this is a perfect topology to kind of utilize to identify how we can influence what links are going to be active, what links are not going to be active. We'll take a look at how this relates to Ether channel and how Ether channel is affected when we're implementing spanning tree as well. Something that we kind of talked about briefly in our Ether channel discussions and lessons. All right. The spanning tree operation does not really define the flow of traffic through the network. I mean, it does and it doesn't, right? Because we go through a process, and we'll talk about the spanning tree algorithm and how that election process works. But certain links are going to be disabled and certain links are going to be enabled. We call that forwarding or discarding, depending on the mode of spanning tree that we're running. But in the end, if, say, for example, in this particular case, our layer 2 forwarding path is not really dictated by spanning tree. So let's say switch 1 ends up being the root in our topology. It's likely that a link there is going to be active, a link there is going to be active, and a link there is going to be active, which means these links are no longer active. Now, in this case, it's a little bit misleading because you look at this topology and this link would be inactive as well. In this case, you look at the topology and you say, yeah, well, of course, all of the traffic from switch to switch has to flow through the root. But that's not always the case. It is possible, for example, by manipulating values or priorities or whatever it might be, that this path might be active, right? That path is active, that path is active, and that path is active. And in this particular case, traffic flowing from switch 4 to switch 3 does not have to go up to the root and then flow back down to switch 3. That's not the purpose of spanning tree. So when I say that spanning tree has some influence on the path selection, that is true in a sense that links are being disabled and enabled. But once the topology has been determined, if there is a direct path between two different switches in the topology, then those two switches can communicate. The whole point here, though, is that we're trying to create some sort of fault-tolerant network, but which requires redundant physical connections. But we still have to have, especially from a layer 2 perspective, we still have to have a loop-free path between all the nodes in the network. It's extremely important. All right? We use a process called the spanning tree algorithm to calculate that loop-free path. All right? So let me talk a little bit about the spanning tree algorithm. We'll get into this in detail a little bit later on. All the devices that are participating within the spanning tree topology, this is run typically per VLAN. The only exception to that would be if I'm using MST. The STA runs not per VLAN, but per instance, not per VLAN. So we'll talk about multiple spanning tree a little bit later on. Our switches, any device that operates at layer 2 is going to run spanning tree. And we send and receive spanning tree frames, and the spanning tree frame that we use in the process of electing the root and going through the whole process is something called a bridge protocol data unit. Come on, data unit, or a Bpdu, all right? And if we look at, let me go back to this wiki here. If I look at this spanning tree wiki, you can see, I wish it was expanded here. You can see that there is a specific MAC address that is used for spanning tree. I was hoping to see it here. Let me see if I can see it from another capture. Spanning tree, Bpdu, Wireshark. These frames, they're sent out on a periodic basis, and I'm looking specifically for one that has the layer 2 information. That's a multiple spanning tree one. Here we go. All right. So this is what I was looking for. It's not a very good image, but let me see if this is a better image. Not really. Let me see if I load it. If it'll be a better image here. Actually, this is exactly what I was looking for. Okay. So if you take a look at this image, you can see that the specific destination for spanning tree Bpdus is sent to this specific MAC address. But notice in this case, we're not using Ethernet 2 as our transport protocol. We're using 802.3 Ethernet as our transport protocol. So we already have a slight difference in how most Ethernet frames are processed in with Bpdus. The MAC address that we're using, 0180C20000000, is reserved for the spanning tree process. That's not a Cisco specific MAC address, but it is a reserved MAC address for this process. You'll notice that there is no layer 3 component to this. In fact, if you look at the LLC component, one of the DSAP and the SSAP is going to be a Bpdu. So spanning tree is carried directly on top of layer 2. And the clients and the switches, they're designed to listen for the spanning tree Bpdus at this, on this particular MAC address. All of the components of spanning tree, let me copy this image. Open up a different one. All of the components of spanning tree, all the pieces that you guys need to understand, are listed here inside the Bpdu. So by the time we're done with our discussion today, you're going to understand what these flags represent. You're going to understand what this represents, what the root ID represents, the bridge ID, port ID, all these different timers. We're going to talk about all of these aspects as part of our discussion of spanning tree. This is actually not a very good image because it doesn't include a lot of the pieces that I actually want to look at. So let me see if this includes. Nope, that's not expanded either. We'll get there. I'll talk to you guys about the individual components within the Bpdu. I've told you guys this before in other lessons. In order for you to truly become an expert, you need to be able to analyze things at the packet level and at the frame level. That's the only way you're going to be able to effectively troubleshoot, design, implement, and whatnot. Okay? So we have multiple active paths in our topology that's going to cause a loop in the network. If a loop exists, of course, the frames are going to be processed and passed through the network topology infinitely, right? Because there's no time to live field or anything within a layer 2 frame. So the spanning tree allows us to define what the topology is going to look like. It allows us to create this loop-free path from the root to all of the other devices within the layer 2 topology. All right? Now, the root itself actually denotes or connotes a couple of different things, right? The bridge on the network that's actually going to serve as the central point in our spanning tree election process, what we call the root device, and also a port on the device that provides the most efficient path for that particular device to get to the root. That's what we call a root port. They're completely distinctly different concepts, and we'll get into what the difference is between those concepts as we go through the algorithm. All right? Any bridge whose role in the network is the root device may not necessarily, or you know, may have some configurations where that might influence the decision for that device to become a root, may not become the root because of the election process. So we need to understand what that election process is, and we'll take a look at that. All right? Any of the redundant paths that exist in the topology Those paths are going to go into a blocked state. There's two primary states in spanning tree, forwarding and blocking. In order for us to effectively get rid of the layer 2 loops in the topology, but still allow those links to be utilized and enabled in the event that a primary path might go down. All right. And our goal in this particular lesson is just to kind of go through that process. What is the election process? We'll take a look at how we can influence that process. We'll run through some configuration examples. I'll show you, how we can verify spanning tree operations within our topology and how we can influence the election process. All right. So the bridge or the switches in our topology, they're going to run what we call per VLAN spanning tree. Let me talk a little bit about different spanning tree technologies. All right. Now, back in the day, IEEE developed a common spanning tree protocol called 802.1d. And the D in this case means don't use this version. All right. That's a joke, obviously, but it's actually kind of true. Because, well, let me ask you guys, what do you think it means if I say it's a common spanning tree protocol? Any ideas? Any thoughts on that? Okay. I was asking, what do you think it means when I say 802.1d is a common spanning tree protocol? That was a good guess, but incorrect. A for effort, though. All right. So oftentimes we are running multiple VLANs in our topology. Right. Common spanning tree, or what we call CST, means that all VLANs have to assume the same STP topology. In other words, we don't have any control of how spanning tree operates on a per VLAN basis. So if I have 100 VLANs, let me go back to my topology here. If I have 100 different VLANs in my topology here, and this guy is the root for VLAN 1, it's going to have to become the root for all of the VLANs. And that means that my traffic flow can't be load balanced. I can't share the link's bandwidth and so on. So that's one reason why 802.1d is not generally recommended, is because it is a common spanning tree protocol. Now, what Cisco did is Cisco went through the process of developing well, actually, before I do that, let me demonstrate or talk about another downside to 802.1d, and that is convergence with 802.1d is extremely slow. And I'm not going to get into, maybe not this time, maybe in a future lesson I'll get into the specifics of how convergence works. But essentially it takes about 30 to 50 seconds to converge whenever there's a topology change. Which, that is, relatively speaking, in networking terms, that is an exorbitant amount of time. So what Cisco did is Cisco developed their own version of 802.1d, and that was called PVST+, which stands for Per VLAN Spanning Tree Plus. All right. Still had slow convergence. So we're still talking about 30 to 50 seconds convergence times. with this particular spanning tree version. But we are able to control spanning tree on a per VLAN basis. This happens to be the default STP mode on Cisco switches. Is this per VLAN spanning tree plus. The plus actually refers to stuff that we're going to talk about in our next lesson. Refers to things like port fast, Bpdu guard, root guard, loop guard, and a whole bunch of other things. Ether channel guard, all those things. Basically, what we call the spanning tree toolkit. And that's our next lesson, is to talk about all of those enhancements to spanning tree that allow spanning tree to operate more efficiently and so on. All right? We still had a limitation here with PVST Plus, though, in that it was still slow, but it did allow us to manage spanning tree on a per VLAN basis, and so we could effectively load share traffic across multiple switches by influencing the election process of spanning tree across those multiple switches. And then the IEEE developed another common spanning tree protocol, which was called 802.1W. The W means rapid spanning tree. All right? Obviously not, but it's an easy way to remember it. That means it's fast. All right? It's still a common spanning tree, so we still have that limitation. But convergence is, about anywhere from 1 to 3 seconds, so considerably faster than, say, your 802.1D, which is extremely slow. Still had some limitations with a common spanning tree, meaning that we could only have one topology, but much, much faster. All right? And then finally, there's one more after this, Cisco developed RPVST Plus. Takes all of the characteristics of per VLAN spanning tree and adds speed. All right, so we can now control spanning tree on a per VLAN basis. We still have all of the other features like port fast and Bpdu filter, Bpdu guard, uplink fast, backbone fast. There's a whole bunch of different tools, and then we're also adding the speed. So this is really the recommended mode at a minimum. Now, the downside to this particular mode of operation is it's extremely processor intensive compared to the IEEE counterpart. And that has to do with the fact that we're managing the STP process per VLAN. So I'm generating Bpdus every 2 seconds on every port per VLAN. So it can be a lot of information, a lot of traffic being generated, and so on. So the last thing that happened is Cisco and IEEE got together and they developed MST. MST stands for multiple spanning tree. It is based on RPVST Plus in that it includes all of the fast timers and the convergence time is relatively quick, but it reduces the overhead significantly. So let's say that we have 100 VLANs in our topology. And if I'm running per VLAN spanning tree or I'm running rapid per VLAN spanning tree, that equals 100 instances of the STP protocol if I'm doing things like PVST Plus or RPVST Plus. But if you look at a topology, usually in a topology, it doesn't quite look like this. This topology is used for educational purposes, but our topology is typically going to look like something like this, where I have, core or collapsed core. I've got my access layer, and this guy is, DSW1, and it might be the root for some VLANs. This guy is DSW2, and it might be the root for some other VLANs. The point is that we only have two switches that are acting as the roots in our topology. So even though I might have 100 instances of VLANs and spanning tree running, I really only need 2 instances because I'm only trying to influence who's going to become the root based on the fact that I only have 2 distribution layer switches. So that's what multiple spanning tree provided us the ability to do. It allowed us to, and we'll see this configuration later on, but it provided us the ability, provides the ability to create STP instances and then associate VLANs to those instances. So instead of having 100 different instances of spanning tree running, I would have 3 instances in our example. You've got instance 0, which is the default instance. That always has to exist. Then I might create instance 1 for VLANs 1 through 50. Then I might create instance 2 for VLANs 51 through 100. So that means that I'm essentially running 3 instances of spanning tree, and I'm able to influence how the election works per instance. So any VLAN that gets tied to an instance of spanning tree assumes that particular topology based on the configuration. We're going to have a lesson on multiple spanning tree in our next session. Actually, probably not the next session, the one after that. Okay, and we'll talk about 802.1s. I didn't even tell you that it was 802.1s. 802.1s, multi-instance or multiple spanning tree. It's actually technically called multiple spanning tree. All right, so those are some of the terms. This is kind of the progression. I don't know that you're really going to be tested on that necessarily on the exam, but I'll keep this in this document so you guys can reference it a little bit later. All right, but so the default instance always has to exist for VLANs that aren't assigned to another specific instance. Because remember, whether or not the VLAN is active in the domain, we have to assume that all the VLANs are there. So if you have a VLAN that's active across your trunk ports or active within the domain and it hasn't been assigned to an instance, it's going to go into instance 0. And you can configure instance 0. You can identify who's the root for instance 0 and who's the backup root for instance 0. But there has to be a placeholder for those VLANs that we didn't explicitly identify within a particular instance. That's really important. All right, and yes, correct. And you can't get rid of instance 0. It always exists, and any VLAN that's not, if you've implemented MST, any VLAN that's not part of another instance is automatically going to go into instance 0. Okay? And we'll see that. We're going to do a whole lesson on MST. I mean, that's fine. I'm glad you're asking questions. That's awesome. But we're going to revisit this. We'll actually configure it. We'll play with it, and I'll show you how that works and so on. All right? STP is turned on by default on switches. And the default mode is PDST+, which is the 802.d variant that Cisco provides. It's going to be active even if I don't have any VLANs configured on my device. Well, the fact is we really don't have a situation where we don't have any VLANs, right? there's always at least some VLAN on the switch, which is VLAN 1. So if I do a quick show VLAN here, we have our configuration left over from the last class. So let me just do a no VLAN 50, 60, 100, 1000, 2000. All right. Oh, dang it. We're using BTP version 3. Let me switch this to BTP version 1. Oh, gosh. Let's do this. I'm not sure if this will work or not. It might not delete the VLANs, but let's see if this works. All right, what I wanted to show you is that the spanning tree is enabled on the switch by default, and of course we already know based on our VLAN discussion that VLAN 1 always exists within spanning tree. All right, config t hostname sw1. Oops. Show VLAN. I'm not concerned about the VLANs being there because we do a show BTP status. We're still running BTP version 3. That's because that's stored in vlan.dat. And the problem is I can't delete / vlan.dat because this is GNS3. So let's just work with this. I mean, it doesn't really matter that we have the VLANs there or not. Let's change. You guys remember how we changed the server, this device, to the primary server? You guys remember the command? We talked about that last time. BTP primary. I guess I could do it for all. What did I make the password? I forgot what I made the password. Maybe it was CCIE. It's thinking. If not, I'll just delete the switch. And it did. All right. So this is a primary. So now I can do a show VLAN. Show VLAN. And I'll do no VLAN 50. Oops, no VLAN 50, 60. Remember, in VTP version 3, we talked about this in the last lesson. Unless I'm the primary server within the VTP domain, I can't modify the VLAN. That might actually be something that pops up on the troubleshooting portion of the exam, right? Where you're trying to add a VLAN or delete a VLAN and it won't allow you to do that. Make sure you verify the VTP operations and make sure that this is the primary server within the VTP domain if you're running VTP version 3. So let's get rid of 100, 1000, and 2000 as well. And do a show VLAN. So I should have my default database here. And that should actually propagate. Oops, I got 1003 as well. That's okay, I can't get rid of that one. So we're good. We've got all of our standard VLANs. I'm going to do a quick show interface trunk, make sure the VLANs are running over the trunk. We're still using ISL, interface range. Because I deleted the config, now using ISL, I don't want that to happen. So let me do Ethernet 0-1 and Ethernet 2/0-1. Switch port trunk encapsulation. Q. Switch port trunk. All right. So anyway, I'm just kind of doing my basic verification. Whenever we're talking about VLANs, we always want to make sure that the domain is set up correctly. So if I do a show VLAN and I do a show interface trunk, I can see that essentially all the VLANs are allowed across the trunk. I'm doing .1Q encapsulation. The only VLAN that's actually active in the management domain is VLAN 1, but it's being pruned because we don't actually have an SVI for VLAN 1. We don't have any active ports in VLAN 1. We have ports in VLAN 1, but we don't actually have any active ports in VLAN 1. Now, eventually, that might show up. So why did it not show up in this case? When I did a show VLAN, we see VLANs in spanning tree forwarding state and not pruned, none. And then when I showed the command again, VLANs in spanning tree forwarding state and not pruned is now VLAN 1. You guys remember what caused that? We saw this in the last lesson. Right? Well, what happened was spanning tree was going through its process of listening, learning, trying to identify whether or not the particular ports on this switch should go into a forwarding state. So if I do a show spanning tree, which is the primary command that we use to verify spanning tree operations, I can see several different things. IEEE means I'm running the Cisco version of 802.1d. I don't know why they just didn't call it PBST. But we'll talk about bridge priority in a little bit. We'll talk about MAC address. And I can see that all my ports are in a forwarding state. We'll get into the details here about what all these numbers mean and why it's important. The point that I'm trying to make in this particular case is that spanning tree is enabled by default on the switch. All right? And it's running on all the interfaces on that switch. There may be instances where spanning tree is disabled, or maybe it's not functioning correctly. That can cause some serious issues in our topology. But we'll actually simulate some of that a little bit later on. So in 802.1d, we have a single instance of spanning tree. But obviously, we're going to convert our information over to our system is going to operate 802.1w a little bit later on. All right, so let's talk about some of the key spanning tree concepts when it comes to the election process and how we perform the election. All right? So I'm going to go back up here, and this is all going to be under the topic of spanning tree algorithm. To enable the STA to proceed with an election process, there has to be a determination of /election of a root switch. All right? Now I'm going to break this down piece by piece. But in order for us to understand how that election process plays out, we also need to understand what is the primary piece that's used to perform that function. And the primary piece, element, in determining who becomes the root is a bridge ID. All right? Now I'm going to talk about this. I don't want to jump too far ahead, but the bridge ID is extremely important when we're determining who becomes the root in our spanning tree topology. So here we go. STA algorithm broken down. All right? It's a 47-step process. We're only about 38 minutes in, so we should be able to get through all 47 steps by the time our 2 hours is up. But we'll start with step number 1. All right? Step 1. Huh? Was that funny? Is that a good joke? Step 1. Elect the root. All right? Always step number 1. This is done on a per VLAN basis. In fact, pretty much everything in spanning tree is done on a per VLAN basis, especially when we're running PBST. The root bridge, which we will call from this point forward the RB, is selected based on 2 values. One is, and this is the primary value, the bridge priority, which is a value that you can set from 0 essentially all the way up to 65,000 let's see. I think it's 65,535. Well, it depends, right? In the Cisco world, yeah, it should still be. No, it doesn't quite go up that high in Cisco. Let me see. Spanning tree, VLAN 1, priority, 61,440. Okay, so we can go all the way up to 61,440. It's 65,535, depending on whether or not you're using an extended system ID or not. But we'll talk about that a little bit later on as well. All right. So this is how you control spanning tree, by establishing the priority of the switch. Second value is the bridge MAC address. Yes, sir. Lowest always wins in spanning tree for everything. Lowest always wins in spanning tree. The bridge MAC address. I'm sorry? No, it can be 0. That's those. Yep. Yep. You can use 0. Lowest always wins in spanning tree. Now, there are 2 different formats for the bridge ID. And I'm only mentioning this, it's probably not going to be on the test, it's probably not going to be something that you have to know, but there are 2 different formats of a bridge ID. Okay? There is the standard format, which is essentially priority.mac. And then there's what we call the extended system ID format, which is priority.systemid.mac. All right, and this is a 16-bit field followed by a 48-bit field. And this is a 4-bit field followed by a 12-bit field followed by a 48-bit field. So in both cases, they're the same size. And there's a reason that's that way, because we want this extended ID format to be backwards compatible with the original standard format of a bridge ID. Why do you think that middle field happens to be 12 bits? What else happens to be 12 bits that's related to spanning tree? Vlan Id Fields. If you look at an 802.1q tag, the Vlan ID field in a .1q tag is 12 bits. So guess what goes in that particular piece of the bridge ID? The VLAN. All right. In fact, let me pull up a picture of a spanning tree bridge ID. Type. This is, yeah, here we go. This is exactly what I want to see. Where did it go? Okay, so this is the original format. You've got bridge priority followed by MAC address, 2 bytes followed by 6 bytes, 16 bits, 48 bits. And what Cisco did is they said, you know what, we want to go ahead and implement spanning tree per VLAN. So there has to be a way for us to be able to identify what VLAN this spanning tree instance is running for. And that's where the extended system ID comes into play. So if I'm running spanning tree for VLAN 1, the value of this field is going to be 1. If I'm running spanning tree for VLAN 10, the value of this field is going to be 10. What that did, though, is that decreased the amount of bits that I had available to me for the bridge priority down to 4 bits. But rather than renumber that field, what Cisco did is they decided that in order to maintain backwards compatibility, they decided that rather than renumber that field, they were going to go ahead and continue the value of those bits, the weight of those decimal places, so instead of starting at 0 here and doing 1, 2, 4, or 1, 2, 4, 8, or whatever, they decided to use 4096, 8192, 16384, and 32768. That's why when you're setting spanning tree priority values on a Cisco device, you have to do it in increments of 4096. And that's why the top value that you can set is 61440. Right, if I take all 16 bits here, if I take 2 to the power of 16, we know that's 65,536. But if I take 32768 and I add 16384 and I add 8192 and I add 4096, I'm going to get my 61440. So that's how they got that top end of the scale. It can still be 0 because if you set those 4 bits to 0, the priority is in fact 0. But the next priority that you can set is 4096. In fact, if I go back to my switch here, you can see it says right here, the bridge priority needs to be entered in increments of 4096. Now you can actually change that behavior. I don't know if this is going to allow us to do it. Extend, let me see, system ID, yep. So let me see if this works. I don't know if it'll work, but I can take out that feature. I can say not accepted because I'm running BTB that permits extended VLANs. All right, so I can disable that feature and just say, okay, no spanning tree extended system ID, meaning that I'm going to go ahead and use the standard format. But there's really no reason to ever do that. You pretty much want to utilize that extended format because you're going to be running spanning tree for VLAN. Another important aspect to understand is that all switches, not just Cisco, the default priority on Cisco switches, and I'll tell you it's actually applicable to any switch. I've seen this on Dell, I've seen this on HP, is 32,768 by default. So that means out of the box, you are relying on MAC address as the deciding factor for who becomes the root, and because lowest wins, that's usually the oldest switch. It's not something you really want to happen. All right, so we always want to be able to influence how our spanning tree topology looks based on identifying the priority for that particular switch. Now, if I come into switch 1 and I do a show spanning tree, I can see that I'm running spanning tree on VLAN 1. This bridge happens to be the root. I'm going to take some of these values here. What you see in this particular output, if I run a show spanning tree, I can do show spanning tree and I can put in a specific VLAN if I want to see a specific VLAN, or I can just hit return and it'll scroll through all the active VLANs on the switch. What you're seeing in the first section of this output is the root's information, and what you're seeing in the second section of this output is your information. I happen to be the root because my MAC address is this, so let me go ahead and copy this MAC address, and we're going to put that in our topology. Let me get rid of that other stuff over there. All right, we already know that the default priority is 32,768, and the MAC address on this particular switch is, oh, there it goes. Come on. Seriously. My computer's running really slow today for some reason. is this MAC address right here. Okay? So whenever I'm trying to evaluate spanning tree, the very first step in evaluating how spanning tree works is to always look at those two values on the switches. So let's go ahead and do the same thing on switch number 2. So let me see if I have, I'm going to have some different VLANs here, but I don't really care about that. Let's do show spanning tree VLAN 1. Oops. And I'll grab the switch's information here. So there's the MAC address of that switch. Go back to my topology, put in that information. So again, 32.768, and that's the MAC address for that switch. Now I can already see why switch 1 would win in this particular case, because the MAC address of switch 1, which should have another 0 there, the MAC address of switch 1 is lower than the MAC address of switch 2. And I think we can pretty much infer what switch 3 is going to be. These are MAC addresses that are assigned by GNS3. It's going to be 300, and switch 4 is going to be 400. All right? So as we're going through our analysis, we're going to go ahead and apply onto this particular topology, and I'll save the diagram for you guys. But we're going to apply on this particular topology what interfaces are functioning, what interfaces are running, what role a particular port takes, and so on. And we will oops, try that again. I'm going to try and make this so that I can save it later. Okay. So we'll use, let me put some designations in here. This will be my root port. This will be my, actually we'll make those green. And orange will be my designated ports. And red will be my blocking ports. Those are the 3 types of ports that we're going to have in this topology. Blocking ports, designated ports, and root ports, as we go through the election process. Root ports, designated ports, blocking ports. That's ultimately what we're going to have to decide in this topology based on our understanding of how the spanning tree algorithm works. So the first thing we have to decide is who became the root. And we know that this switch became the root because of the criteria that we're using to elect that root. And that criteria is based on priority and MAC address. Because the priority was the same on all the switches in the VLAN, then the MAC address became the tiebreaker. And switch 1 because it won because it had the lowest MAC address. So this is a very easy step to understand. Now let me see if there's anything else I want to add to this description here. Done per VLAN, the root bridge is selected based on 2 values. The bridge priority, that's how you control spanning tree. The bridge MAC address. Lowest always wins in spanning tree. There are 2 different formats for the bridge ID. The default priority on the switch is 32.768. That means out of the box you're relying on a MAC address as the deciding factor of who becomes the root. A couple ways you can see that MAC address, by the way. You can do a show spanning tree, or you can do a show version. And usually in the show version, it doesn't work in GNS3, but at the end of the show version, you'll see a reference to something called the base MAC address. And that base MAC address is burned into the motherboard. But a show spanning tree will also very quickly give you the MAC address that's used in the spanning tree process. There's only one MAC address used in spanning tree. That's the base MAC address of the device. So did you guys have any questions about step number 1? All right. Everybody understands. Step 2, elect the root ports, which are forwarding ports in spanning tree. All right? This is done on every switch that is not the root. Okay? And the way that we define root ports, we select the root port based on the least cost path, based on the port that provides the least cost path to the root bridge. All right, now what does that actually mean? IEEE has defined path cost values on specific interface types. And you can actually see in my show spanning tree output, you can see the cost defined here. So let me pull up what those costs look like. And I'll put them in the notepad as well. So essentially, there's actually two different variations of this. I'm going to reference the one that you would most likely see on the exam. I'm also going to reference the one that we see in spanning tree. So IEEE and GNS3, STP path cost values. So there's a couple of different references here. It depends on whether or not you're using kind of a more modern version of spanning tree. You can see these path cost values are significantly different than what you see on the right here. What you're most likely going to see is these values on the right. A 10 gig link is going to cost you 2. A 1 gig link is going to cost you 4. A 100 meg link is going to cost you 19. We don't care about 16. A 10 meg link is going to cost you 100, and so on. So you can see that the path cost values are going to go down based on the actual speeds of the links. And so this used to be the old values, meaning that anything above a gig looked essentially the same. But the new values allow us to differentiate between 10 gig, 1 gig, and so on. All right, so let me put that into Notepad. So a 10 megabit link is going to cost you 100. A 100 megabit link is going to cost you 19. A 1 gigabit link is going to cost you 4. And a 10 gigabit link is going to cost you 2. Now you might look at that and say, well, wait a minute. What if I have stuff that's faster than 10 gig? Well, they do have new definitions. 10 terabits is going to cost you 2. 1 terabit, 20. 100 gig, 200, and so on. So they have defined, as part of the update to spanning tree, new values. But you can see based on our spanning tree output that we're using the traditional values. That's why I'm going to reference those in this example. All right? So now if I take a look at my topology diagram, I can start to reference those path costs on each of these links. So let's say this interface has a path cost of 100. This interface has a path cost of 100. All of them do, right? I don't guess I need to put them all in here, but might as well to be consistent. Now we can influence that value. We can actually change that value. I'll show you how we do that a little bit later on to change how the topology is going to look in spanning tree. We already saw in our ether channel discussion on our previous lesson that by bonding links together, you're actually reducing the cost of those links because you're getting cumulative bandwidth between those two different links. So we don't have any active ether channels. I don't believe we have any active ether channels. We shouldn't. In our topology. Show ether channel summary. Nope, no active ether channels. So if I do a show spanning tree, I can see that all of the interfaces have a path cost of 100. So let's take a look at this from the perspective of switch number 2. Switch 2 has multiple ways that it can get to the root. It can go this way, and that's going to give me a cost of 100. It can go that way, that's going to give me a cost of 100. It can go this way, which is going to give me a cost of 300. It's a cumulative path cost, right? I can go this way, which is a cost of 200, and so on. So basically what switch 2 is doing is it's going through an analysis and saying, okay, which port am I going to prefer to get to the root? And that's based on total path cost. So the cumulative path cost is what determines, IEEE's defined path cost. We select the root port based on the port that provides the least cumulative path cost to the root. Okay? Now, we have a bit of a problem. And our problem is, what if there's a tie? And there is a tie in this case. I think everybody agrees we're definitely going to go over one of these two interfaces here. Agreed? So we're definitely going to go over one of those two interfaces here. But I have to select only one port as a root port. Unless this was an ether channel and these links were bonded together, only one of these interfaces can become a root port in our topology. All right? So that's really important to understand. Let me do one more thing as part of this process here. Try and kind of make it a little bit easier to put these designations on these interfaces. All right? I'm not going to make it pretty. You guys get the idea. All right? So there is a tiebreaker based on that selection process. And that tiebreaker has to do with something called port priority. Let me type it in real quick. That didn't work out very well. That's fine. All right, I'll get the other ones in a little bit. So what if there are two paths to the root bridge with the same path cost through the same neighbor? That's really important, right? In this case, it is the same neighbor. It's switch 1. What do I do? I select the port that is receiving, this is very important, receiving the lowest reported port priority from the neighbor. All right? And let me show you what port priority looks like. You'll notice that every interface on the switch has a priority value. 128 dot something. So the dot 1, the dot 2, the dot 3, that's equivalent to something like a MAC address, whereas that's directly tied to the physical port number, the interface number, but the 128 is a value that you can modify. That's almost like setting the priority on a switch. So I can influence switch 1, I can influence how switch 2 decides to get to switch 1 by changing the port priorities on switch 1, which then get advertised over to switch 2. Now, if I look at the port priorities in this particular case, Ethernet 00 has a port priority of 128.1. Sorry, I want the 20. 128.9. So this switch is advertising a port priority of 128.9 on that interface and 128.10 on this interface. So because of that, out of both of those values, which port is switch 2 going to select as its root port? Two zero. That's right. We're going to select 20 as my root port. Let me change the color, and let's fill that little puppy in. That's good enough. All right, So that becomes my root port. All right. I don't like the way that looks. Let me just do this. MS Paint is not always the best tool to use, but kind of gets the job done. All right. And I can even put the designation on there. That is my root port for that switch. Now let's see if we can go back and verify that. If I go to switch 2, and I type show spanning tree, VLAN 1, which is going to show me exactly what I just saw, I can in fact see that port 20 is a root port. And it's in a forwarding state. This is the cost. So Ethernet 20 is how I get to the root in this particular topology. What if I wanted to change that? Well, let's say that I wanted to make interface Ethernet 2.1 the preferred path. I would go into the interface and I would say spanning tree port priority, and I can modify the priority from 0 to 192 in increments of 64. So if I just simply say 64, now this switch is advertising a lower priority for that interface, and what should happen on this switch is the root port should switch. So now it's going through the listening state. So it did switch over to 2.1. It's going through the listening state, then it's going to go through the learning state, and then finally it'll eventually go into the forwarding state. That's kind of the downside to 802.1d spanning tree is we have all these different states that we're going through to determine whether or not. And by the way, we stay in those states for 15 seconds. That's what the forwarding delay value is. The listening and learning states are statically configured to operate for 15 seconds. So at a minimum, we're not going to be forwarding for 30 seconds. All right, now we're finally forwarding. That became my root port. All right, I'm going to take that off because I want to make sure that we have kind of a standard topology based on our diagram. That's how I can influence how path is selected. Now let's look at this from the perspective of switch 3. I think it's going to be pretty clear from the perspective of switch 3 how that's going to look. Based on our understanding of how port priorities work, which port is going to become the root port on switch 3? Isn't it just basically the lowest port number from the other switch's side? So if this is Ethernet 1.0 and this is Ethernet 1.1, we're going to be advertising a lower priority on Ethernet 1.0 based on the interface number. So the root port for switch 3 is going to become Ethernet 1.0. All right? Are you guys following me so far? Let's go into switch 3 and just verify that. Show spanning tree. And Ethernet 1.0 is a root port. Now let's look at this from the perspective of switch number 4. If I go this direction, it's going to be a cost of 200. If I go this direction, it's a cost of 100. If I go this direction, it's a cost of 200. So clearly I'm going to go up the diagonal links to get to the root. Again, which interface are we going to select? It's by default going to be based on lowest port number from the neighboring side. All right. But let's assume, for argument's sake, that those diagonal links are not enabled. All right, we're going to keep them enabled for the purposes of our discussion, but let's assume that they're not there. How would I decide which way to go? The problem that I have in that scenario is that there's another tie in this case. And that tie is, do I go to switch 3 or do I go to switch 2? Because the cost is the same in both directions. What do you think we do to break that tie? There always has to be a tiebreaker in spanning tree. There can never be a tie within spanning tree. So what do you think I'm going to do to break that tie? I have to make a decision. Ken asked a question. Why does the priority have to be in increments of 64? That's a good question. I'm not, actually, I know why. I'm getting a little echo, so mute yourself. If you look at the priority value of an interface, Cisco identifies the interface by a physical number. And I don't know, well, I guess specifically we would be able to calculate it, right? If we're talking about increments of 64, let me just use this to take some notes here. That means that 1, 2, 3, 4, that'd be 1, 2, 4, 8, 16, 32. That means that the interface number must be a value that's represented by 5 bits. 1, 2, 8, 4, 1, 2, 4, 8, 16, and 32. And the priority starts after that, but they didn't start the renumbering. So just like we had with the bridge priority, the port priority gets set starting in the 64 column. So the first number you can set is 0, the second number is 64, and it goes all the way up to 192, which means that in this case, that should be 8 bits, right? So actually, I did one too many. Because this is the 64 column, this is the 128 column. Actually, 1, 2, 4, 8, 16, 32, 64, 128. That's as far as I need to go. So that's kind of interesting. That means that yeah, that makes sense. So we can be 64, but it can be 0. It can be 64, it can be 128, or it can be 192. So we only have 3 values that we can select. That's my guess. I mean, it makes sense mathematically based on how we talk about priority being set as well. All right? Hope that answered your question, Kim. So I posed a question. In the case we have a tiebreaker, what do we do about that tie? Do I go to switch 2 or do I go to switch 3? Both paths have the same path cost. Somebody was going to offer an answer. Go ahead. I'll let you guys offer an answer. Anybody? Which direction do you think I'm going to go? There has to be, I have to make a decision. I'm going to choose the neighbor with the lowest bridge ID. So I'm going to go up to switch number 2. Because the bridge ID for switch number 2 is lower than the bridge ID for switch number 3. It kind of makes sense because ultimately switch 2 most likely would become the root if switch 1 failed because it has the second lowest bridge ID. So we're actually kind of planning ahead. Now, based on the fact that we're going to choose the switch with the lowest bridge ID, let me put this in the notes real quick. Let's see. The question was, what if there are 2 paths to the root bridge with the same path cost through the different neighbors? I select the path through the neighbor with the lowest bridge ID. Very, very simple. Now in this case we have a couple of different tiebreakers because we have to pick the direction, the general direction, which we've done. And we also have to pick the port. That's going to be based on port priority, as usual. The port priority that's being advertised by switch 2, and in this case, because we're using the defaults, this interface is going to become the root for that switch because that switch port has the lowest port priority. That's the lowest port priority being advertised by the neighbor. Okay? Great. We've got all of our root ports selected. Awesome. All right. Now the next step is to go into step number 3. Only 40 something steps left. Step number 3. Select all of my designated ports, what we call DP. And in this case, we were selecting our root ports, which we would call RP, I guess, to make it simple. All right? Every segment, which are the links between switches, will have at least one, no, actually I can't say that, we'll have one designated port. So based on our topology, how many designated ports will I have in this particular topology based on that statement? How many links do I have? 2, 4, 6, 8, 10, 12, right? Which means I'm going to have 12 designated ports. I just realized we made the assumption that this middle link was not active, but it is. So we're not going to set that as our root port. Our root port should actually technically be 0, 0 on the switch, because that has a lower total path cost to the root. You guys understand the change, right? I was going through the scenario of trying to demonstrate what happens if we have an equal cost path through 2 different neighbors. But those diagonal links are definitely active, so we don't have to necessarily. That's going to be the lowest path cost because it's 100. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 segments. Every segment in our topology is going to have a designated port. Every single one. The selection process for that is really, really simple. The port on the segment that is connected to the switch with the lowest bridge ID wins. All right? And guess who always wins? The root bridge always wins because it always has the lowest bridge ID. So all ports on the root switch, on the root bridge, will be designated. Okay? So let's go ahead and put that on our diagram because it's never going to lose. Right? The root will never lose that election. So let me grab my orange dots here, and I'm going to make every single interface on the root designated. All right? Very, very simple rule. Every segment has to have one of these orange dots. And those are all of my designated ports. What about the diagonal link here between switch 3 and switch 2? Which side is going to become designated in this particular case? Is it switch 2 or switch 3? Switch 2 is going to become designated. Right? Because switch 2 has the lowest bridge ID. 0200 is less than 0300. All right? So I will go ahead and put in my designated ports for switch 2. Both ports become designated because they're both going to win. What about the ports between switch 2 and switch 4? Again, switch 2 is going to win because it has the lowest bridge ID on that segment. So I've identified what the status is of all the ports on switch 1. I've identified what the status is of almost all the ports on switch 2. But what about all these other ports? Well, that brings us to our final step, okay, which is really, really simple. Step 4, what we call non-designated ports, or blocking ports. And we'll just call these block. These were DP. These are my blocking ports. Essentially, in this case, everything else is blocking / discarding. It depends on your spanning tree designation, whether it's called blocking or discarding. All right? So now that we're done with this process, we should be able to identify that we now no longer have any loops in our topology. So this port is going to block. These 2 ports, well, this port will block as well. That's a big block. Basically anything that's left over. Oops, I forgot something on this switch, didn't I? Between switch 3 and switch 4, we don't have our designated ports. We know that switch 3 is going to win because it has the lowest bridge ID between the 2 switches. So let me go ahead and add my blocking ports. I'll go back and add the designated ports on that side. All right. And these 2 ports are going to be in a blocking state. And we've got our designated ports now on this side. Every port in this topology now has a designation. Oops, I forgot to block those 2. We'll get there eventually, guys. We'll get there. And then we're going to go back and verify that our math is correct and everything was done correctly as part of the process. Blocking port there. And a blocking port there. As long as you follow these 4 steps, regardless of the actual version of spanning tree, because they all use the same algorithm, as long as you follow these steps, you'll always be able to determine which links are active and which links are not active based on the spanning tree topology. So let me go ahead and put in, so this link is no longer active. Let's make that a lighter color. This link is no longer active. These 2 links are no longer active. They're still physically plugged in, but they're not used for forwarding traffic. And these 2 links are no longer active. And finally, 2 more actually. That link's not going to be active. I forgot to add my red dot there. We'll go ahead and add that. And this link is not active. There's my red dot there. Did we get rid of all the loops? Absolutely. We got rid of all the loops in the topology. So let's go through switch by switch and verify that the topology matches what we expect it to match. And certainly on the exam, the written exam, you might be presented with a topology that you have to identify, what ports are designated, what ports are non-designated, and so on. Or you might, in the actual lab, they might actually make you this, configure spanning tree so that certain ports are active and certain ports are not active in the topology. So let's go to switch 1 and verify that, in fact, all the ports are designated. Show spanning tree. And sure enough, all the ports are designated on switch 1. On switch 2, only 2.0 should be a root port, 2.1 should be a blocking port, and all the remaining ports should be designated. So 2.0 is our root port, 2.1 is our blocking port, and we can see that, well, let me just run the command again. We can see that from right here. Oh, forgot we have a bunch of extra VLANs on this one. We can see that right here. 2.0 is my root port, 2.1 is a blocking port, and the rest of my ports are designated ports. If I look at my topology diagram again, switch 3, the root port should be 1.0, and 2.0 and 2.1 should be designated. 0.0 and 0.1 should be blocking. So let's go to switch 3. Show spanning tree VLAN 1. And sure enough, 0.0 and 0.1 are blocking. 0.2 is designated, 3 is designated, 1.0 is my root, 1.1 is blocking. I don't think we're using 1.1 in our topology here. Oh, we are, yep, and it is blocking, that's what it should be. And 2.0 and 2.1 should be designated. Sure enough, 2.0 and 2.1 are designated. The reason why these other ports show up is because in GNS3, the ports are enabled by default, and they, even though they don't have a device connected to them, the link status still shows as enabled in up. So it's kind of misreporting that information. Finally, we'll verify switch 4. All ports are blocking in our topology. 1.0, 1.1, 0.0, 0.1, 2.0, 2.1, or certain 0.0 is a root port. So let's go ahead and check. Show spanning tree VLAN 1, and sure enough, 0.0 is my root port, 0.1 is blocking, 2.0 is blocking, 2.1 is blocking. That matches with what we see in our topology. All right, and 1.0 and 1.1 should also be blocking. Let's just verify that. 1.0, yep, blocking, and 1.1 is blocking. It's amazing how that works. Right? That is the spanning tree algorithm. And that's really all there is to it. Now, it does change a little bit when you start to get into multiple spanning tree. But essentially with multiple spanning tree, the instances use the same process to determine who's the root for a particular instance. And when we get into our multiple spanning tree discussion, we'll talk about that. All right? Now let's go back and take a look at our spanning tree Bpdu, because we have been talking quite a bit about a lot of these different pieces of spanning tree. So if we look at a spanning tree Bpdu, we can now really kind of start to identify what's contained within the Bpdu itself. In fact, let me see if I can find one that has all of the fields expanded. Trying to find one that has, I don't really want to use an MST one because it has some extra stuff in there that we don't really need to see. Right here. Perfect. Right? So when you look at and you break down a spanning tree Bpdu, it's pretty simple. Now that you understand what all the terminology represents. The protocol ID is STP protocol. We're running rapid spanning tree in this particular case. So the Bpdu type is going to be a rapid spanning tree MST Bpdu. Remember, MST, multiple spanning tree, uses rapid spanning tree as its foundation protocol to be able to pass Bpdu information. These are the flags that were concealed previously, but remember, these Bpdus are being sent out of a specific interface. This is the interface ID right here, hex 8017. So you take that priority value and that interface number value, convert it to a decimal equivalent, and then convert that value to hex, and you'll be able to get the port ID. And these are the flags that are set. 3C means that the port is forwarding. It's currently learning, so the learning state is active, and it's designated, meaning that it's assumed a role of designated. Learning means that we're not technically forwarding frames out this port yet, but we're actually updating our MAC address table as frames come in. I know it's a little bit misleading because it does indicate that it's forwarding. Actually, in this case, we're converged. Because a forwarding port would also be learning, right? I mean, that's a normal port operation. There is the potential of seeing forwarding no, but learning yes, if we're going through the process of negotiating our spanning tree topology. The port role is designated. We're not sending out any TCNs or topology change notification packets or frames. And then this is the root's information. That's the priority of the root. That's the VLAN. So we know that this is a Bpdu for VLAN 10. That's the base MAC address of the root. That's the root's priority. The VLAN base MAC address. The path cost to the root is 0 because I am the root. You look at the MAC address, it matches. So I'm actually the root for this particular VLAN. And that's why this port is designated, because all ports on the root bridge are designated. All right, max age timer indicates as part of the transition process within spanning tree, if I'm not receiving Bpdus on an interface, the max age timer allows me to identify essentially how long I'm going to wait before I start progressing through the other spanning tree states. The hello time is how often I'm sending Bpdus, which is every 2 seconds. And then the forwarding delay is how long I'm going to stay in, say, the listening and the learning states, which is 15 seconds by default. Okay? Now, we've gone through the whole election process, but I do want to talk a little bit about the timers that we see here. Right? We already said that the hello timer determines how often the bridge is going to broadcast out the hello messages or the Bpdus to other devices. You can actually change those values. It's not really recommended, but you can change those values. The forwarding delay timer allows us to determine how long each of the listening and learning states last before the interface either goes into a permanent forwarding state or goes into a blocking state. And then the max age timer is how much time am I going to actually store protocol information received on a particular interface. That also happens to be the timer that needs to expire before I decide that I'm going to progress into the listening and the learning states if, for example, I plug a PC into a port. All right? So we talk about how spanning tree runs on switches, but spanning tree can also run on access points as well, wireless bridges, because they're a layer 2 device. So there's one other thing I need to show you. We've got about a half an hour left before we wrap up this lesson. There's one other thing I wanted to show you before we wrap it up. But before I do that, I want to talk a little bit about these different states. Now, it depends on the implementation of spanning tree. A blocking port, that's pretty obvious to understand. The blocking port is not going to be participating in any type of frame forwarding for the spanning tree topology. It doesn't mean that it's a permanently blocked port, because if there's a topology change, a blocking port can become a forwarding port. We also have a listening state. This is the first transitional state after the blocking state is done. So if I plug a PC into a port, I'm going to stay in the blocking state until that max age timer expires, and then I'm going to move into this listening state. Essentially, in listening state, what I'm trying to determine is how the interface should participate in spanning tree. Is it going to be a forwarding interface? Is it going to be a blocking interface? So I'm listening for Bpdus. But the port is still not forwarding data traffic. The learning state, the interface is preparing itself to participate in forwarding. It's not forwarding traffic, it's still blocking traffic, but it's updating its MAC address table for frames that it receives on that particular interface. That's why it's called the learning state, because we're learning our MAC addresses in this particular state. Forwarding means, of course, that the interface has decided to act as a forwarding interface, and we're forwarding traffic normally. All right? So, and then Cisco always defines this. I never understood why, but they always define a final state, which is disabled. That means that the interface is actually not running spanning tree because the port is shut down. To me, that's like, why? How could that be a spanning tree mode if the port's not running spanning tree? But anyway. So when you plug a device into a port, the interface itself transitions through the blocking state and moves from blocking to listening, and then it moves from listening to learning, and then it will move from learning to forwarding or back to blocking, depending on whether or not the port needs to be blocked based on the spanning tree process, the spanning tree election process. All right? When you enable spanning tree, obviously we need to stabilize the topology by getting to those permanent states of either forwarding or blocking. Now, rapid spanning tree, we'll talk more about rapid spanning tree in our next lesson, because that's what the next lesson is reserved for. Actually removes one of these particular states. It doesn't do the listening state. It only does the learning state. All right? Trying to think if there's anything else I need to kind of mention. I'll just say really quickly, if an interface is in blocking state, it's participating in spanning tree, but it's still discarding any frames it receives on the port. It doesn't learn MAC addresses. But even though it's discarding frames it receives on the port, it still receives Bpdus. It still processes Bpdus. In the listening state, it's essentially the same thing. We're discarding frames on the port. We don't learn MAC addresses, and we're still receiving Bpdus. In the learning state, the only difference is we're learning MAC addresses. Okay? So the only thing left is to kind of talk about how we manipulate spanning tree. But we've already seen some of the settings that we can modify, right? We can modify port priority to influence maybe how a neighbor decides to reach me through the spanning tree topology. Let's say that I wanted to make, in our topology, I wanted to make switch 3 the root for VLAN 1, but only VLAN 1. And I want to make switch 4 the root for VLAN 2. Well, we'll just call it 2. Okay? I'll have to create VLAN 2. And then I want this switch here to be the backup root for VLAN 2. And I want the switch on the right to be the backup root for VLAN 1. Now, there's a couple ways that we can configure this. The simplest way is to use the macro that's built into Cisco. You can go into the switch and you can say config t, spanning tree VLAN 1, root, primary. This is a macro that once I execute this command, based on all the information that switch 2 has already learned, it's going to go ahead and set the priority of switch 2 to 2 decrements below what the lowest priority it learned on the topology. That was not a very good way of saying that. If it's 32.768, if I do a show spanning tree VLAN 1, do show spanning tree VLAN 1, you can see that the priority has been decremented to 24.576. And this switch is now the root for VLAN 1. Well, if I take 24.576, let's do 32.768 minus 4,096 minus 4,096, I get 24.576. So that's what I was trying to describe. We set the priority to 2 decrements below whatever the lowest priority you received was. Now, what if somebody on the network already has a priority of 4,096? What happens in this case? If there's another switch that has a priority of 4096, then I can only decrement my one value down to 0. What if there's another switch in the topology that has a priority of 0 already? Well, I can only decrement to 0. I can't go below 0. So I will decrement to 0, and then I'll rely on the MAC address to be my tiebreaker. Okay? This command actually results in the configuration of an actual priority being set for the VLAN. Okay, spanning tree VLAN 1, priority 24576. So I could also execute that command if I so chose. I could say, instead of allowing the macro to decide what the priority is going to be, I'm going to go ahead and statically configure the priority. Now, remember, we wanted this guy to be the backup route for VLAN 2. Spanning tree VLAN 2, route secondary. Do show spanning tree VLAN 2. It's not running because I don't have VLAN 2, so let me create VLAN 2. Let's do BTP primary. The only downside, of course, to using BTP version 3. All right. Config T VLAN 2. All right. Show spanning tree VLAN 2. And you can see, well, it says this bridge is the route for VLAN 2, but you can see the priority was set to 28672. All right. So it set it to one less than the default, 32768. So that's how we effectively influence the spanning tree election process, by establishing who's going to be the root per VLAN. All right? Let me see, is there anything else I want to talk about just in this introductory session? Yes. No, it still matters. It just means you're not using the extended system ID format. So, yeah. So if you're not using the extended system ID format, then you don't have to use increments of 4096. And the bridge with a priority of 0 is going to win in the spanning tree election process. It provides you the ability to run spanning tree per VLAN. Yeah. If you want to manipulate who's going to become the root per VLAN, you have to implement, you have to utilize the extended system ID format, because that's how the VLAN is identified in the spanning tree Bpdu, is based on that extended system ID field within the Bpdu. So, yeah. All right. Now you may also check. I couldn't turn it off on this switch because I'm running VTP version 3. Let me see if I can VTP version 1. Now this one let me change it. So I just want to see, do a show VTP status. Let me go to version 1. That's okay. I don't need version 1. What I wanted to see is if I could do spanning tree, no spanning tree, extended system ID. All right. Oh, show VLAN. Oh, no VLAN 2000. No VLAN 1000. So do show spanning tree. So you can see even though I've disabled that extended system ID function, it still recognizes the system ID for VLAN 1, and it's taking the priority and it's adding the VLAN number on top of the priority. So I'm guessing that in your Nexus environment, that if you did a show spanning tree, you would see that the priority is not, the priorities are still being set per VLAN. There's one other thing I wanted to check. Spanning tree VLAN 2 priority. Yeah, so that command did not disable the spanning tree mode. I would have to probably change the mode. Spanning tree mode. Yeah, see, I can't even set the mode to 802.1d. So my guess, and the Nexus might be a little bit different, but my guess is that it's allowing you to put a 0 and a 1 because it's not requiring you to implement the priority in an extended system ID format. That would be my guess. All right, but do a quick show spanning. Yeah, do a show spanning tree on the switch and see if the extended system ID is even represented in the show spanning tree output. That's the default on Nexus. It's not the default on iOS-based switches. The default is IEEE, which is PBST. If I want to switch to rapid mode, I will use the spanning tree mode rapid command, and that will change me to rapid spanning tree protocol. Okay, they are compatible. The versions are compatible with each other, so you can run mixed mode environments, but you're not going to get all the efficiencies of rapid spanning tree if you've got some non-rapid spanning tree switches in the topology. Much more efficient. Correct. But you can't just simply enable MST. So I can't just come in here and say spanning tree mode MST. It'll take the command, and if I do a show spanning tree, it shows that the protocol is MSTP, and you can see the path costs go to the new version. But until you've actually configured the MST instances and the process, there's several different configurations that need to be included. You have to set up the domain, you have to set up the revision number, a bunch of other things that need to be configured in order to run MSTP. But we'll go through that in our process. So it looks like I just turned it on, but I'm still running spanning tree. Notice here that the system ID changed from a 1 to a 0. Right? So if I do a show MST, show spanning tree MST, excuse me, I have a lot of different options. I can look at the configuration, and I can see that I really don't have a configuration. The revision number is not configured. The name of the MST instance is not configured. But because we have that default instance, it put everything into instance 0. So in order for MST to be effective, because we basically just converted our entire spanning tree topology to common spanning tree, because everybody has to take the topology that's defined with instance 0. So when it comes to configuring MST, you have to set up the instances, you have to map the VLANs to the appropriate instances, and then turn on MST, and then everything will work as expected. But it is definitely the recommended approach, because if you have thousands of VLANs and you only have 2 instances, you're only going to be running 2 instances of spanning tree. Does that make sense? Or 3, because zero is always going to exist. So it's much, much more efficient.